In this video, we will address the dynamics of mechanical systems. We will introduce several concepts needed to the analysis of structural dynamics, such as eigenmodes, eigenfrequencies, or modal projection. Our subject is an elastic solid that we consider in this study as isolated from the outside. Let us first describe the local dynamics of this elastic solid contained in the domain omega s. Let us assume that this solid is at equilibrium and steady and consider a short and local perturbation. Imagine the impact of a hammer, for instance. This will create several waves propagating to the edge and reflecting. The analysis on a short time consists in describing the waves generated by the perturbation. At long time, the multiple reflection will generate a complex kinematics that is not easy to describe mathematically. We need an analytical framework for the global study of this system. This framework is called modal analysis. We first present some classical systems in structural dynamics. We will not demonstrate the equations here. Some of the set of equations given in this video are presented in a little more detail in another video. Before starting, it should be noted that we are looking at displacements and deformations that are small enough to consider a linear study. Moreover, we will neglect any form of dissipation in the system. The systems of partial differential equations presented in this video can all be put in a form where a mass operator m and a stiffness operator k are applied to a vector or scalar field noted here xi. Xi is most often a displacement field. An external forcing F, vector or scalar, can be exerted on the system. The system must be completed by a set of boundary conditions on the edge of the solid domain. Let us start with the very simple and classical case of the tension string. Consider a flexible string of linear mass μ stretched between two fixed points and subjected to a tension T. The kinematic variable here is the displacement field perpendicular to the segment of the string at equilibrium. It is noted W and depends on the abscissa x and on time. The mass operator consists of a product by the Linec mass. The stiffness operator is minus t times the second derivative in space. F is a scalar field of linear forced distribution, which possibly depends on time. In the case of the slender Euler-Bernoulli beam, the stiffness force do not come from tension, but from a bending stiffness of the structure. We consider a beam of length L and any cross-section. The material constituting the beam has a Young's modulus E and the mass per unit length is noted μ. We will assume a problem where the displacement of the sections is only along y and the rotation of the sections is around z. Displacement is again a scalar which depends on x and time. The mass operator is the multiplication by the mass per unit length μ, and the stiffness operator is EI times the first derivative in x of the displacement. I is here the moment of inertia of the section. It is a parameter that depends on the geometry of the section and is equal to the integral over the section of y squared. For the clamp-free beam shown here, we define these four boundary conditions. And finally, the external forcing is a linear distribution of vertical force F. Let us look at the more general case of 3D linear and isotropic elasticity. The field xi is a three-component vector field which depends on space and time, defined on omega s. The mass operator is a multiplication by the density ρs, and the stiffness operator involves the successive gradients and divergence of the displacement field. The boundary conditions can be, for example, an imposed displacement at the interface, in the case of a clamp, or zero stress on the free surface. And finally, the external forces correspond to a distribution of volumic force on omega s or surface force on the interface. Finally, With these three examples, we have illustrated that the undamped dynamics of mechanical systems can be generalized in a form involving a mass operator, a stiffness operator, boundary conditions, and an external forcing. Now that we have presented the general problems, we will identify in the solution of these systems of equations the eigenmodes and eigenfrequencies. Let's start by doing a linear experiment. Using a microphone, we record the pressure signal generated at a point in space by the vibration of one of these structures after a shock. The time signal is plotted like an oscilloscope on the left, and a Fourier analysis is shown on the right. We can see that for all the experiments, the dynamics is dominated by isolated harmonic components. Let's highlight this on the simple and classical case of the vibrating string. The dynamic equations are rewritten here by noting c the speed of the wave in a string. And as a reminder, the boundary conditions always consist in imposing a zero displacement at the end. We now look for separate variable solutions of the form f of x times g of t, and we introduce this solution into the equations of the problem. By putting all time-dependent terms on the left and space-dependent term on the right, we show that they must necessarily be equal to a constant, which we call minus omega square. The solutions for g and f then take the form of a sum of a sine and a cosine. Using the boundary conditions, we then show that the constant in front of the cosine is 0, and that k can only take certain values that can be put in the form of a discrete series n pi on L, with n a positive integer. There is thus an infinite number of solutions of this problem, which we indicate here by n. This solution gives the frequency omega n, which relates to the wave number by omega n equals c times kn. To summarize, the solutions f of x that we have just identified are called eigenmodes of the system. They will be noted in the following phi n. They are defined to a constant Cn. The complete solution of the system is therefore a linear combination of these eigenmodes depending on time as an harmonic function at the frequency omega n. The constants an and bn depend on the initial conditions of the system. It can be, for example, the amplitude and its time derivative at t equals 0. Note that it's often more convenient to write the solution as a sum of complex harmonics of which we take the real part. This writing is strictly equivalent with complex dn constants. Let us now briefly look at the case of the clamped free beam. We simply expose the eigenmodes and eigenfrequencies. These are parameterized by the family of numbers lambda n, which is given by the solutions of the transcendental equation cosine lambda n times hyperbolic cosine lambda n plus 1 equals 0. Let us return to the problem of finding eigenmodes and eigenfrequencies, starting from the general case. Given the form of the mass operator of the problem, involving a second derivative in time only, we can directly search for complex harmonic solutions of this system in the form of phi of c times the exponential of I omega t. The introduction of the solution into the dynamics equation gives, when combined with boundary condition at the edge of the domain, an eigenvalue problem called the Sturm-Liouville problem. We will assume that we can compute the solutions of this system of equation either by analytical calculation or by performing an approximate calculation using numerical methods. We thus have for each system an infinite family of eigenmodes and eigenfrequencies. It should be noted that the mechanical problem posed here is not specific to the dynamics of structures. By writing the dynamics of an inviscid fluid in a rectangular tank, we also obtain a Sturm-Liouville system, whose eigenmodes can be calculated. The oscillation of the free surface according to some of these eigenmodes is shown in this animation. In acoustics also, as for example in this parallelepipedic room, we can highlight eigenmodes and eigenfrequencies. Now that we have identified the eigenmodes of mechanical systems, let us see how they can be used to solve the general dynamics. First of all, we will show that these modes form an orthogonal basis. Let's start by defining a scalar product of the functions defined on omega s. The scalar product of f by g is defined as the integral of the product of f times g on the domain. Is this product bilinear? It is. Is it positive? It is. Is it symmetric? It is still the case. So we are dealing with a scalar product. Let us also assume that the mass and stiffness operator are self-adjoint, which means that the operator applied to f scalar g is equal to f scalar the operator applied to g. Finally, we assume that m and k are positive definite. Note that for all basic mechanical systems, m and k always verify these assumptions. This may not be the case for some system in fluid structure interaction, for example. Once these assumptions and verifications are made, we can define a scalar product in the sense of the mass and scalar product in the sense of the stiffness. We will now show that the modes form an orthogonal basis. Let phi and phi be two eigenmodes associated to the frequency omega p and omega q. They therefore satisfy the following equations. Let us project the first equation on phi q and the second on phi p. We then make the difference between the two equations, and if the operators are self-adjoint, we easily arrived at the following relation: omega p squared minus omega q squared times the scalar product of phi and phi q with respect to mass operator equals 0. We can therefore conclude that for two different eigenfrequencies, the scalar product is 0. Thus, we can say that the eigenmodes are orthogonal in the sense of the mass operator. We can deduce directly that the modes are also orthogonal with respect to the stiffness operator. If p is equal to q, then the scalar products are not 0, and we call them modal mass and modal stiffness. We saw earlier that these eigenmodes were defined to within a multiplicative constant. Just as we would do with the eigenvectors of an eigenvalue problem in a vector space, we can fix the constant by choosing a norm. Several choices are possible. One of them is to fix the modal mass equal to unity. As a consequence, we obtain the following orthogonality relation. The scalar product with respect to mass of phi and phi q equals 1 if p equals q and 0 otherwise, and consequently, the scalar product with respect to the stiffness of phi and phi q is 0 if p is different from q and equals omega p squared if p equals q. We are thus dealing with an orthonormal basis of infinite dimension. We will now use this orthonormal basis called modal basis to describe the dynamics of the mechanical system. We start from the equation of the force dynamics in a generic form written here with a scalar field psi and f for simplicity. Let us make a modal expansion of the solution field, that is to say that we represent it as an infinite sum of eigenmodes. The coefficients of the sum of the phi modes depend on time and are denoted qp. For some conciseness, we adopt this more compact writing. We introduce this decomposition of the solution in the dynamics equation, and we make the projection of this equation on a mode phi n. In other words, we make a scalar product of all the terms with phi n. Since the scalar product is an integral in space, we can get time-dependent terms out, as well as the sum. Next, if we use the orthogonality properties defined earlier, we obtain an ordinary differential equation with only the variable qm. It is a classical equation of an harmonic oscillator of mass mn, of stiffness kn, on which a force Fn is exerted, where Fn is the projection of the external forces distribution on mode n. It is called the modal force. The solutions of this oscillator equation are well known. Let us summarize what we have just shown. We are interested in this type of dynamic equation where a mass operator, a stiffness operator, and a time-dependent force distribution appear. It describes the dynamics in the form of a set of partial differential equations, boundary conditions, and initial conditions. We make the modal decomposition and we project the equation on the modes to obtain an infinite number of oscillator equations. We are in a modal space. The unknowns are the modal displacements, and we now have an infinite number of ordinary differential equations in time that we know well since they are harmonic oscillator equations. Note that in practice the system is only solved for a finite number of modes capital N. The relevant number of modes to retain is determined by the spatial scales of interest or the frequencies we wish to retain in the dynamics. Solving the harmonic oscillator equations is not a major problem, and the solution of the initial problem is obtained by recombining the contributions of each mode. The use of the modal basis representation thus facilitates a resolution which was not obvious in the initial physical domain. Before ending, I propose to illustrate the principle of modal-based resolution in the case of the vibrating strings without external forcing. The dynamic equation is recalled here, written in a form in which appears the phase velocity of the waves and in which the mass operator is unitary. The modal basis is given by the set of functions square root of 2 sine n pi x over L. This coefficient square root of 2 allows to have an orthonormal basis. Indeed, the scalar product in the sense of mass is simply written in this case as the integral between 0 and L of the product phi p phi n, which is 1 if the amplitude of the modes is equal to square root of 2. The particular problem we are going to solve is that of a plucked string. That is to say that it's pulled from its equilibrium position at any point, then released at t equals 0. The initial condition is noted W0 of x. It can be decomposed as a sum of the eigenmodes, the coefficients being noted Q0 n. The fact that we are dealing with an orthonormal basis allows us to determine the set of coefficients Q0 n simply by projecting the initial condition W0 onto each mode. Here is a representation of these coefficients for the initial condition drawn on the left. In order to highlight the notion of truncation, which consists in selecting only a finite number of modes, let us draw a superposition of the exact initial condition and its representation using an increasing number of modes. The greater the number of modes, the better the representation of the initial condition. We can determine the truncation criterion based on the physical representation we want for the pinch point, for example. Now that we have determined the initial condition of each oscillator, we can determine the modal displacement n as Q0 n times cosine omega n t. And the modal recomposition gives the solution of the problem in physical space. Here is the practical implementation of this solution. On the top left, we have the initial condition. At the top right, we have the time evolution of each oscillator. At the bottom right, we have the contribution of each mode, that is Qn of t times phi n of x. And at the bottom left, the modal recombination. And one can easily deal with the other initial condition, since it simply implies to compute the initial condition of the oscillators. This quick introduction to the basic principle of modal analysis is over. We can now use this principle for any mechanical system for which we know the eigenmodes and eigenfrequencies. Here is the example of a rectangular plate struck at a point. For this simulation, the first 400 modes have been retained. To go further, the question of damping present in all real systems should be addressed. But let us remember that for low dissipative systems and for some standard form of damping, the eigenmodes resulting from an analysis without damping are still valid. It should be noted that the modal analysis can also be used to study discrete systems, such as this pendulum. In this case, we are not dealing with an infinite dimensional space, the dimension being this time the number of degrees of freedom of the system. These are vector space, and the mass and stiffness operators are then matrix operators. Discrete systems can also result from a discretization of a complex continuous system, which is a prerequisite for solving the system with a computer. This is the case when the finite element method is used to discretize the differential operators of an elastic solid, such as this clamped free beam. The case of discrete system will be the subject of another video. This is the end of this video. Thank you and see you soon.